Okay, last time we saw the vector diagram for the pendulum, simple pendulum, okay? Now we've got one for a ball or cart on a ramp. So that's either the ball or a wheel of the cart, okay? Anyhow, assume it's a ball, and you've got I'll label it on this side. The weight, which I'll indicate by the vector W. Again, a vector just has a magnitude and a direction. Okay? So you've got the weight. Now, this thing has a mass, which we'll call M. And the weight is just M times G, where G is the acceleration of gravity, the rate at which gravity causes velocity to change. So, stuck on there. If I take this object and drop it, it accelerates, and all objects accelerate at the same rate. I say all objects, all particles that accelerate without interference, that fall freely, without air resistance, without somebody hitting them with a baseball bat or a fly swatter. Okay? So that's a concept that hopefully you saw in science classes in middle school, but don't know. So you got the gravitational acceleration vector G. Newton's second law says that force is mass times acceleration, right? So this is just net gravitational force, we'll say it's mass times acceleration. That's not the net force on the mass unless you remove the ramp and evacuate the air. Okay? But that is the force that's being exerted. That's a force that's pushing this thing downward or pulling it downward. Okay? Now, we know that this mass accelerates along the incline, not straight down. That's because of a force exerted by the incline. Okay? And we also can demonstrate, can you have me that meter stick on? Maybe not totally convincingly, but maybe at least plausibly. Let's see, I don't think I have any money. I'll use a magnet. Okay, I'll watch the magnet's the same color as that. Or I'll just use a piece of chalk. I can get it to stay still. Flatten it out a little bit. There we go. Now, might be a bad choice. There's that flat spot again. It's a bit flatter. Okay? Now, if gravity, if this thing's a lot heavier, has much more mass, gravity will pull down on it harder. So let's just pretend it does have more mass. So gravity's pulled down here, right? When I release this thing, what will be the path of the chalk?
Perpendicular to the ramp.
Perpendicular to the ramp, not straight up. People often say straight up, but I think you're right. Let's just check. Oh, missed it.
More or less straight up.
Didn't miss it by much, but I wasn't trying that hard. It wasn't straight up. Landed all the way over here. How How'd it land all the way over here? What was its path?
It wasn't a straight path.
Well, you know, there's the ramp, here's the chalk, it's released here, it lands here, goes about this high. It's a parabolic path, and we'll prove that. I mean, we can observe it, okay? And with a little more regulation, we can actually establish that you do get a parabolic path. And the reasons for that, I'm not going to get into yet. Okay? Now, that's the way I drew the parabolic path. I'm not sure I drew a good right angle here, but this should be a right angle. Okay? If you go back to the video and look at the blurs, you'll see that it's pretty much a right angle. Depending on, you know, I think you get 30 frames per second, depending on where the relevant frames are. Path is going to start out very close to perpendicular, and then it's going to go into parabola. I think I've got a little too straight here. It wasn't a great parabola. Okay? And I'm going to say a little more about that parabolic path, and I want you to internalize this. You have a constant velocity in the x direction. And if you track this, you know, stopping the video every click, and do that a few times, you'll hit it in different points and you'll get a pretty good picture of where it is, and maybe a convincing picture that the velocity in the horizontal direction, it moves across the board at the same speed at every point. Now that's not strictly true because there's a little bit of air resistance, so it does change a little bit. Okay? But it's not moving that fast. There's not that much air resistance. It's fairly dense, not really exactly streamlined, but there's not much change in the horizontal velocity, and if there was no air, there wouldn't be any. Because there's no force in that direction. If there's no air resistance, there's no force acting in that direction. Gravity is acting perpendicular to this. Gravity acts only in this direction. Gravity can't change the speed in that direction. Okay? So I'll comment that gravity exerts force only in the vertical. Bad V there, but only in the vertical direction. Okay? So what happens is we start off with quite a bit of vertical speed, which decreases, reaches zero here, and then increases in the downward direction. Okay? And it decreases at a constant rate. WRT stands for with respect to time. Because gravitational force is constant. Okay? So, there's a connection there. It's because of Newton's second law, which says force equals mass times acceleration. That force is the gravitational force. So the acceleration is gravitational force divided by the mass. Okay, we're not actually using that right now unless I give you pretty explicit instructions to do it, but pretty soon we're going to assume that you know to use that when the time comes. Okay? So anyhow, now this is a little bit of an aside, but the main thing I wanted to show here is that the force is perpendicular. Well, this thing is bending that ramp a little bit. So when the ramp springs back, if it was to spring back, it would produce a force perpendicular to the ramp. That's called a normal force. Okay? So we have a force here. And it's perpendicular to the incline. Now, if you're on a road with a car, the incline doesn't really bend, it compresses. But those compressive forces are symmetric around the wheels, and they still push back perpendicular to the incline. A little bit of an oversimplified statement, but it's pretty close to the truth. Okay? So you have this and you have this. These forces can't be in equilibrium any more than the two pendulum forces can be in equilibrium. They're not parallel. If you have a rubber band pulling down here and a rubber band pulling down here, pulling up here, they're going to tend to snap back and give you a net force in this direction. And that net force here is just equal to the component of this force perpendicular to the ramp. So that this force is equivalent to this force combined with this force. If you replaced this rubber band, okay, rubber band in this direction, with a force this big in this direction and this big in this direction, it would have exactly the same effect as this force. Okay? So what I'm going to do is I'm going to draw a little cross out, a little squiggly cross out. So this force is gone, and now we've replaced it by these two. Okay? This force is equal and opposite to this force. So the normal force is just what you need in order to keep these two forces in equilibrium. They have to be in equilibrium. They have to be equal and opposite because there's no acceleration along this line. Acceleration's along this line, and this line's perpendicular to it. Okay? So there's no acceleration in this direction, so all the forces in this direction have to add up to zero. Okay? So I'm going to say there's no acceleration perpendicular to the incline, so this force is equal and opposite to this force. Okay? That makes sense? Yeah, it's not a familiar idea. You're not used to thinking in terms of that idea unless you've had some physics that discussed it. Okay? Hopefully it would. And usually it isn't explained quite that way, but because it's just in a high school physics class, it's just kind of decreed, and maybe you talk about it a little bit. Okay? Teaching physics and engineers used to say that's the way it is. Okay? I don't, but a lot of times that's kind of the way it's taught. Okay, so these are equal and opposite, so this is the net force. Now, if the incline is steeper, then you have to go further out along this line to project this back, right? In other words, steeper and steeper ramps you get less and less of this and more of this. I didn't exactly draw that well. That one's actually quite a bit bigger than I drew it, but it's less than it is here. So this normal force becomes less, and this net force becomes greater. Okay? Now we're assuming that there's no friction. So there's friction, then there's a little force back this way that slows the thing down. For the ball and the incline, that's rolling friction, but there's actually static friction as well, and we'll talk about that later. So this is the ideal case, and if there's no friction, the ball doesn't even roll, it just slides. Nothing to make it roll. No frictional force to make it tumble. So, you know, and then you get this, so you get this force here, but now to project it over here, you gotta go all the way over here, so this force gets even bigger, and this force gets even smaller. Make sense? Well, I'm gonna ask you to draw maybe 4 good pictures. Okay? And then the payoff for this is on the ramp, that means no friction and the ramp is straight. F net equals constant, okay? So mx double prime is constant, so x double prime equals F net over M is constant. Okay? So F prime just antiderivative of F net over M with respect to T. And that equals simple antiderivative, right? Much easier than what you have for a pendulum, because you can immediately verify that the derivative of this is this, right? And x equals antiderivative of x prime, which is F net over 2m times t squared. plus C1t plus C2, where C2 is a constant.
Do I need anything to take home?
No, I'll have to email you. So what you need to do is email me. You get an email this evening, if you email me. Okay, let me just make a final comment here. These three equations tell you what the velocity function is, tell you what the position function is. Position function quadratic, the velocity function is linear, just like the graphs that you got for position and angular velocity when we counted the ramp. Okay? So you want to understand all that.